Why do we care about it? So let's consider, I know, GL and C acting on X. So I know here A matrix goes to GA GX. Orbits. So what are the orbits? How many orbits do we have? It's the same answer as before. N plus 1. And
no,
what is
no,
the-
no, no. These are semi-simple.
But what about
No, it's not
the values?
Maar de characteristic worden nou.
Oh, okay. No, I want to ask.
That normal form.
Yes.
No, this is not. So what is it they wanted? Maybe just this one. No.
Well, maybe JLN acting.
So maybe
What result do you need?
I want the rank. Okay, am I good now? Okay, so now what is the answer? The invariance for this. Sorry? Yeah, so the orbits. So this is matrices. Rank. Okay. And the thing is that if you have matrices of rank n, as we know, this is an open orbit. This is an open subset. And the unique matrix of order 0, of rank 0, which is the 0 matrix, is a closed thing. And the guys in between are mixed. Or I guess that the rank is semi-continuous. To be of rank less or equal to k is a closed property. To be of rank more than k is an open property, and as we've seen before, this is given by the non-vanishing of a certain determinant. So it is open, and to be of rank k exactly is the intersection of these two sets. Less or equal, more or equal, and these orbits are locally closed. So this conclusion was correct also for the previous example that I was incorrect on the board, because it's too general. I wanted to make it as simple as possible. So this is a theorem by Chevalet. Okay. Yes. There should be accent somewhere, no?
Nowhere.
Over not by clock. Close field. G acts on V algebraically. Orbits are locally closed. And this is for the Zarisk equality, which is the only thing that we have here. And this follows from the more general. So this is something about maybe one of the most basic theorems in the theory of algebraic groups, which again you should know. But it follows from a more general theorem which has nothing to do with groups. V to U, algebraic morphism. So if you look at phi v inside U, so this set is constructible. Again, so it's
which is more than it will imply.
it's less than locally closed. Locally closed is constructible. Constructible is not necessarily locally closed.
What I'm asking is when we will switch to the correct topology.
So when yeah, so this will implies this implies yeah, when if we take a field which is both algebraically closed and as a finite topology which comes from an absolute value, like the complex number, maybe like CP, then those theorems will, we will get versions of those theorems for orbits for G acting on V over that field for free. Because locally closed for the Zariski topology is certainly locally closed for the finite topology. But we want to have similar theorems for the reals and for the p-adic numbers and for FPT. Okay, so this is why we work. This is basically why I mean, it's not the only reason why it's important, but this is why we bother to develop all the analytic geometry that we did.
So the theorems fail when regarding the Zariski topology, the theorems fail for non-algebraic correspondence?
Possibly yes. So just wait.
Right, because as you said, the positive reals are not constructible in the Zariski topology.
Yes, yes, okay. The positive reals is not constructible set for the Zariski topology over R. It is constructible for the finite topology, which is the usual topology. So where are we? And this is the image of the morphism which is taking the square from R star to R star. But what was I want to say? So I want to say that this theorem implies that one because the orbits. Oh, in fact, both theorems are implied. Or maybe I'll say how this theorem implies that one. So if you have if G acts on V, then I have for every x in V, I have the map G to V taking G to Gx. This is an algebraic map. The image is an orbit. So the image is constructible by that one. But the image also, so as any constructible set, I can present it as a union of U's. So there is UA, and I don't know, union UA, A1, etc., 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 but all points are alike. So all points are in UA. So the orbit is U of the orbit, so it is locally closed. Also, I want to state the following. Both theorems are implied by phi v. Oh, maybe. If phi is dominant, so this means that if I restrict the fancy way to say that people restrict only to the essential image. So I may assume that what PV sees is everything. If he is dominant, then PV always contains an open subset of U. Non-empty. So let me explain how these imply that, for example. So again, I'm looking at the orbit. It contains an open subset of V. Now I'm assuming that, again, V, and the orbit is dense. There is dense in V. So I'm looking at the V orbit, and it contains an open subset which contains a point. So it contains a point of an open neighborhood of a point, but I can shift around all points that I like. So it contains an open subset of an open neighborhood for every point, and the union of these is everything. It must be everything.
But you just said that the orbit is open. I don't understand.
So the orbit is open in its closure, which is locally closed. Yeah, thanks. And how do we prove that out of this fact? So obviously we may always restrict to the dominant case, and then we can also replace V and U by V always contains an open, smooth submanifold, subvariety, so I can restrict to that one. And, or I guess, maybe I should say the following. It is enough, well, I want to assume that V is irreducible. If V is reducible, I will, so it has finitely many irreducible components, and if each has a constructible image, then the union of all is constructible and it's the image of V. So I may assume that V is irreducible. Basically I'm doing it by induction on dimension, or by Noetherian induction if you wish. It is enough to prove it for open subset of V.
You assume that V is Noetherian? That you have finitely many irreducible components?
I'm assuming that I'm doing algebraic geometry over an algebraic closed field here.
No, you
Sorry?
still have infinitely many irreducible components in V.
No. A variety is Noetherian.
Okay.
Yeah.
Right.
Yes. Always assume that a variety is a finite union of, or finitely covered by finite varieties. Yeah. This is part of the definition. And what I want to say, I don't want to write it down. Again, this is all very classical, but I want to say that it is enough for me to prove it for that statement, replacing V with an open subset of V. Because if I show that the image of the open subset is constructible, I will look at the image of the complement, which is something of a smaller dimension. I will get by induction that it is constructible as well. So the union again is constructible. So I can, while proving, I can reduce myself to open subsets. Since I reduce to open subset, and since every variety has an open subset which is smooth, I may assume that V is smooth. And also I may assume that U is smooth just by restricting to an open subset in U, and its per image is another open subset of V, which I intersect by. And then I may further assume that the dimensions of the fiber of V over U are constant. So V basically is a vibration over U, and then okay, and then okay, well, we will not review everything, but then one sees that the differential is non-singular of thing. When moving to a fine coordinates, the differential is not singular, hence the image is open. So this is a bunch of theorems that I'm using. But I said just both to review the standard theorem that we are mimicking, but also because this is indeed what we will mimic later on. I mean, when I want to prove an analog for that, for the K variety. Oops. Okay, so now homomorphism of K varieties. Then the UK is constructible for the capable.
Uri, I have a question back to this. What you said, the various steps, they all seemed not to use the algebraic process of the field. What you sketched so very bit. At which point do you need this? I mean, the reduction you did, somehow I didn't see how this is important. And you know it's important.
Well, it is important in
Maybe for the theorem to hold.
yeah, but
But
I just
somehow
kept the proof, so we.
No, but
I need to
you
read on my-
sketched the proof of the theorem given the fact that phi of E contains an open set.
No, I sketched. I sketched proof that one.
Ah.
As well. No. I said that this is very easy and it's followed by induction. I sketched both.
That would
This was
I was
the
under the
sketch.
impression that that's what you did, that you sketched the induction.
I did both.
Maybe it was too sketchy to see which assumptions are necessary.
Yeah. Yes. Let me sketch. I want to do now. I should think about it. I want to do this now, and let's think while I'm doing it. So here's the analog of that one. So there exists open non-empty K subvariety in U. U0 in U. this lemma to that thing is like this one to that thing. So maybe I'll again explain how this lemma imply that thing, which is the same as reviewing this explanation. So basically, by Noetherianity that I have, so the Noetherianity says that if you look at a chain of proper closed subspaces, every such chain is finite. So by Noetherian induction, I may assume that I prove that theorem for every closed subset, subvariety of U. Okay? So I'm reducing the difficulty from the variety U to closed subvarieties of U. And then if I look at U naught in U, and if its image is constructible for the analytic topology, the complement of U naught is a proper closed subvariety. So its image by the induction assumption is constructible as well. So the image of U, which is the union of the two, is constructible as well. Again, this is that implication.
So previously you used the differential.
Yeah. This was an essential point in, this was very, so this, previously I did mention this explanation, which I consider as full proof of that implication, but then I sketched the proof, this was very, very sketchy, sketch of the proof of that fact. Now, I'm going to explain the proof of that fact in slightly more pedantic way, okay?
And that would use.
And this will use differential, yes. And this will modulo some standard facts from algebraic geometry. It will be complete, the sketch. Or maybe, let me assume the characteristic is 0, and later on remark on that. So now I want to make various reductions. So first reduction is phi is dominant. Again, I'm just drawing from the image everything which I don't see by the map. This is not a problem.
But now when you say dominant, which kind of closure do you take?
Zariski. The dominant is
This always means that.
when I used algebraic geometric terms, I will refer to the Zariski topology. So I will assume that U and V are affine. Again, I may take an affine and irreducible. I do it component by component. This is not a problem. Actually, I'm assuming that U is irreducible, and if the map is dominant, then V is irreducible in any case. And then I can take an affine neighborhood of V and restrict to the play image in U of it, because I just want to show that I can find a nice set in U, and also I can restrict to an affine neighborhood of that, or a affine set in that affine set. So I can assume both are affine. Also, and irreducible, I will assume they are smooth. Again, this is an open condition in H, so I may assume this. And all fibers of phi have the same dimension. So this is V, U, this is the map. It might be that dimension drop at a point. Generically, it is constant, so I just take this generic subset. And maybe I should assume for the very start that V is the closure of its k-point. The k-points are dense. There is k-dense in each. This is again not a serious assumption. Well, there is something you have to know, that if a set of k-points, the heuristic closure of it is defined over k. This is a very standard fact. It's very easy to prove. Characteristic 0, it's true in every characteristic, though the proof gets a bit trickier.
But notation is confusing. U and V are analytic manifolds.
No. There are varieties. So I guess I didn't write all the. So U and V are k varieties. So this means that there are varieties, maybe over the complex numbers, but they are defined. The polynomials that define them are these. And Vk. So basically, I may assume that they sit in some Cn. They are fine. And Vk is just V intersection Rn. Vk is Vr. Is V, which are the complex points, section Rn, right? This is the standard notation. And if you take the intersection of, if you take a bunch of real points, and you take the heuristic closure of this bunch, this will define for you a variety, which is defined over R. But you can define it by real polynomials. This is a very easy exercise to do. And if you solve it over the reals, you realize that what you ever, the solution that you write is correct. Actually, you can, maybe I'll tell you the solution. If you have a polynomial that vanishes on the set, also its complex conjugation vanishes on that set. And you can cook out of these two a real polynomial. So whenever you have a variety, a bunch of k points, I can use the Galois group of k to cook up, to take defining polynomials of the closure and cook out of it polynomials which are defined over k. Okay? It's get a bit complicated in positive characteristic, because then the Galois group, I mean, the algebraic closure and is not a separable closure, and you have problem with the Galois group realizing exactly. I mean, the k points are not. Okay, there is something to prove regarding the points invariant under the fixed points of the Galois group and the k points. Well, they are the same up to this difference between the separable closure and the algebraic closure. So, okay. So you have to deal with that. So this is partially why, but this is not the main part. Why looking now on characteristic 0.
And when you say that all fibers have the same dimension, you want them to be regular at all points.
So I claim that from this it follows that the map is regular at every point. Oh, the map is regular. Oh, now the map is regular on an open set. So again, it follows from that. And regular by means of algebraic geometry, but it is the same. I mean, differential is non-singular.
No, but even before, if you say that the fiber has a dimension, you want the fiber to be a variety. So you want.
I mean, I don't want the fiber to be the variety. Yes, but the fiber is a variety, which is
if it was regular.
Okay, so I claim the map is regular on an open set.
Okay, maybe I'm confused. I thought you want to conclude this from the above.
So, just a minute. So I want to say that D field has full rank. So this happens on. No, it does not follow from the above. I mean,
Okay.
from the above, this follows. The map is regular, it has a full rank on an open set. So this is again a fact of algebraic geometry, which I used here as well, and I sketched that.
Maybe it's my lack of knowledge of algebraic geometry, but just to say that the fiber has a dimension supposes that the fiber has a certain structure.
So okay, so this is.
And if
this
you
is,
just have any map, then the fiber is not a manifold or.
Oh, well, you can always regard it as an algebraic fiber.
Yes, if the map was regular at every point.
Even if it hasn't. Just, but this is not a complete triviality. This is if phi is separable. So this means now I have k v okay u. This is the field of rational functions over kv. This is something of rational functions on v is a separable extension. So this is something that always happens in characteristic 0, which I'm assuming. That maps are always separable. All maps in characteristic 0 are separable, so we don't care about it. And in that case, in characteristic 0, this fact is always true. That maps are regular in an open, useristic open set.
Two questions. First of all, this K is the same K? And when you now refer to regularness, which is an algebraic geometric notion, you
yes.
suddenly think of the K points, or is it
This is the same. If the maps are they are defined over K, then I mean you can tensor it with the algebraic flow thing, and then this will be the same.
Second thing, maybe it relates to Aaron's question. The fact that it's an open set on which the rank is full has to do with your many reductions, right? That you're essentially onto or something.
Yes.
Otherwise, it's.
I mean, for example, if I'm not
if you just embed the A7 in A20, it's not of full rank.
yes.
It is a full rank. No, it is a full rank. So,
This follows from the
it's
standard
not an
setting.
automatic thing.
No, this is not an automatic thing. No, this is automatic things while everything is fine.
Yeah.
I mean, so basically, it's like saying that if this extension is separable, then all the you can cook out of it various extensions over the corresponding local fields, and or the corresponding residue fields, and all these are separable. Okay. I don't want to go into it. I just want to explain the reduction and. I mean, to reduce things to things which are standard. So the fact that we don't know well the standard things, this is our fault. So what was? Okay, so but now after having this, so again, algebraic geometry tells me that on this open set, d phi has a full rank. But this is the same. I mean, as we remarked, I don't know, 2 hours ago or so. This is the same as saying that d phi analytic has a full rank at every point of this set. So, and on this set, the map is open. So it is submersion. Maybe I didn't say it precisely when we discussed submersion. If you have a submersion is an open map. It's locally open map and it's globally open map, and this is exactly what we need for that. Okay, so I think I'm over my time, and I don't want to lose your confidence. So I think that maybe next time I'll review some of the background that I just sketched very loosely now, the algebraic geometry background. I will not prove everything, but I will give you a firmer ground to stand on, and then I will review that and do it in full details. Yes.
אביב היו פה, אתה מתכוון שלי בחיים פה?
So,
כן. אביב היו בארצים שאתה רוצה להראות, שעליהם אתה רואה אותם. אז אביב היו זה ה-K-Points של מה שאתה